Hello, good morning everybody. This is Indra. Welcome back to my channel. Today in this video, I am going to discuss about one very important and interesting topic in engineering mathematics, Laplace transformation. I have already made a separate video on this topic on the basic concept of the Laplace transformation. I will post the link of that video on the description box. Please first watch this video and then you will be very clear about this topic also. Today we will take the Laplace transformation of the exponential signal. Please watch this video till the end so that you will be very clear about how to calculate the Laplace transformation of the exponential signal, as well as some basic idea on the Laplace transformation. And if you don't subscribe my channel yet, please make sure to subscribe it and press the bell icon for instant notification of all the uploaded videos from this channel. Without wasting any further time, let's go ahead. Here, this is the topic of our today's discussion, Laplace transformation. Basically, today we will discuss about the Laplace transformation of the exponential signal. In our previous video, we have discussed about the Laplace transformation of the unit signal 1, and let's do the revision here. The Laplace transformation of 1 is just 1 over s. The value of the s should be greater than 0. Here the Laplace transformation of 1 is just 1 over s, and the s should be greater than 0. We have already derived this relation in the previous video. Let's discuss about the Laplace transformation of exponential signal here. Let's take a function of time. Let's take a signal f of t. It is in the time domain. It is a function of time. Let's take it is in the exponential form, e to the power a t. Here a signal, basically it is the exponential signal, which is represented by f of t. It is the function of time, or it is written in the time domain, and it is here e to the power a t. Let's evaluate its corresponding Laplace transformation. Here this is written in the time domain. This is time domain signal, time domain input signal. Let's take this it as a input, time input signal. Here this signal f of t, it is in the time domain form, and we take it as a input signal. Let's give this input to the Laplace machine, and the Laplace machine is here. This symbol is for the Laplace transformation. Laplace transformation of, let's plug in this input signal on this machine. Laplace transformation of f of t. First of all, let me write the formula. Please remember the basic formula of the Laplace transformation. It is defined as an integral value from 0 to infinite of the function e to the power minus st times here the input is f of t. So we have to take here the input f of t, and the integration is done with respect to the time. Please memorize this formula. This is the formula to find the Laplace transformation of any time domain signal. Let's plug in the value. Here our input signal is f of t is here e to the power at. It is an exponential signal. Let's plug in the place of f of t. 0 to infinity e to the power, this is e to the power negative st, and here the f of t has the value e to the power at. This is dt. Let's use the simple rule of the exponents or the indices. We can simplify this. Let me write here. This can be further written as 0 to infinity e to the power. Here the base is same. Here the base is same e, and they are in the product form, so we can add the powers, and this can be further written as just minus s plus a t. and this is dt. Here we just use the basic rule of the exponents, basic rule of the indices. And here we don't know the value of the a. It is lies in the negative part, or it is 0 or positive. And here the upper bound of the limit is here the infinite. If the value of the s, let's rearrange this again. Let's simplify more. 0 to infinity e to the power, and this can be written as, we can take the minus as the common, s minus a t dt. Here we have taken the minus sign as the common in the exponents. We can write this, and let's simplify more. Let's talk more about here. Here the upper limit is, here the upper limit of the integral is the infinite when this quantity when the s, let me write here, when the value of the s is s minus a, let's say when this quantity s minus a is greater than 0, then this will be positive. If the s minus a is positive, then the e to the power minus t, and this will be just e to the power negative infinite when we plug the value of the t as the infinite. And this is defined, this is exist. The limit does exist here. If this quantity s minus a is positive, if this s minus a is positive, then we can evaluate the corresponding limiting value. The limit exists. The sequence will be converges here. And if when the s minus a is negative, if this is negative, then the negative times negative will be positive. Then here will be the positive number, and e to the power positive infinity will occur there. If s minus a is negative, negative times negative is positive, and if we plug in the value of the t as the infinity, then this will be the e to the power positive infinity, and this does not exist here. This does not exist. We cannot evaluate the limiting value here. The sequence should be diverges, so the limit does not exist. Limit does not exist at this situation. So for the limit to be calculated, for the limiting value to be calculated, or the integral value to be calculated, this should not be happen. So we cannot choose the value of the s minus a less than 0. This for the simplified case, this means s is less than a, it is not possible. This can be rearranged, s minus s less than a. This is impossible. If this happens, then the limit does not exist. So this is not possible. And here this is the possible case, and this implies the value of the s greater than a. Here the condition is, please remember this condition, the value of the s, this value of the s should be greater than, it should be more than a. This is the relation between s and a. So this value of the a is less than, it should be less than the value of the s. And let's move to the previous steps here. Let's continue it. And here we have divided the range. This is the range. Here we have derived the range of the s. It should be greater than a. Value of the s should be greater than a. This is the reason of the convergence. We will discuss about the revision of the convergence later. And here let's continue here, and we can easily find out the limiting the integral value. It is just 0 to infinity e to the power minus s minus a t dt, and the condition is, it is valid for all the s greater than a. It is the condition. It is valid when the value of the s greater than a. We have already discussed about that. And let's evaluate the limit integral value. And this is the integration of the exponential signal is very easy. Same, e to the power minus s minus a t. And here the variable is the t. Here the variable is the t, and the others alphabets are the constant. Here the only t is the variable, others are constant. So here the coefficient of the variable is this quantity minus quantity. So we have to divide this quantity by the coefficient of the variable. Coefficient of the variable is just minus s minus a. This is the process of taking the integration of exponential signal, and here the limit goes from 0 to infinite. Let's rearrange this, and here the 1 over minus 1 over s minus a, this is a constant, so we can take it as a coefficient. And if we plug in the value of the t as the infinite, first we have to take the upper bound. If we put the value of the t as the infinite, this will be e to the power negative infinity minus then the term of the second boundary. And if we plug in the value of the t as the 0, then this will be e to the power just 0. And let's simplify this further. Minus 1 over s minus a, and e to the power negative infinity, this will give the 0. This can be written as 1 over e to the power positive infinity, then that will be the 0. So 0 minus this e to the power 0 is just 1. So this here from we will obtain just minus 1. E to the power negative infinity will be 0 minus this is 1. 0 minus 1 gives minus 1. And this can be further simplified as just minus times minus positive 1 over s minus a. And the condition is, please remember the condition, the value of the s should be greater than a, or the value of the a is less than s. This is the region of the convergence. We will discuss about the region of the convergence later. Here we have just calculate the Laplace transformation of the exponential signal. Finally, let's do the conclusion here. Let's write the conclusion. The Laplace transformation of the exponential signal is here taken as the e to the power at. It is here obtained at just 1 over s minus a. Please remember this very important formula. And the condition is the value of the s greater than a. Here we have obtained this beautiful result. The Laplace transformation of the exponential signal is just 1 over s minus a, and the value of the s should be greater than a. And from this, let's evaluate the condition when the value of the t is 0. When the value of the t is 0, then that will be Laplace transformation of e to the power 0 will be 1. Laplace transformation of 1. We have already derived the Laplace transformation of 1. From these relations, let's check it matches to the previous one or not. Laplace transformation of, here we have just plug in the value of the t as the 0, substituting. Let's substitute the value of the t as the 0. Value of the we cannot take the value of the t as the 0. This is just plug in when the value of the a is 0. When the value of the a is 0, sorry, I mistakenly write this. When the value of the a is 0, then this will be the e to the power 0. E to the power 0 gives just 1. Laplace transformation of 1. And this will be just 1 over s minus, the value of the a is here 0. S minus 0, just s. This matches to the previous derivation. Here from this relation, we have also calculated the Laplace transformation of 1 is the 1 over s. The value of the s should be greater than 0. Here in this lesson we have discussed about the Laplace transformation, basically Laplace transformation of the exponential signal. In our next video we will discuss more about the Laplace transformation of the different types of the signals, different types of the time domain signals, as well as we will apply the Laplace transformation to solve the differential equations also. Please keep watching, keep loving this channel, and if you don't subscribe my channel yet, please subscribe it. We will meet in our the next video. This much for today. Thank you.